I wasn't originally going to do this because one, it's not really a primitive shape, and two, I'm kind of running out of paper to write on, but you know what? I like checking off boxes, so let's add another row and column to this 3D collisions matrix, shall we? I am having way too much fun with this. Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D collisions in GameMaker. So, we've got all of our basic primitive 3D shapes ready to go in this 3D collision system here. We've done a bunch of matrix math that we can use to aid us in our quest in the future, and I think now it is time to start looking at transformed 3D meshes in 3D space and detecting collisions against 3D models that are perhaps not at the world origin. They can have a rotation or a translation. I'm not going to be doing scale. I don't find scale is very useful for detecting collisions against 3D models a lot of the time, but well, also translation and rotation should just keep us busy for long enough anyway. So I'm going to create myself a new code file in the collision shapes folder. I'm going to call this call transformed model. That's a bit of a mouthful. That needs to be marked as a constructor. Collision transformed model is a bit of a mouthful, but I want to make sure that it's sufficiently differentiated from just a regular old triangle mesh, which is just a collection of triangles in a hierarchy without any possible transformation applied to them. So let's get set up. I'm hoping that I'll be able to get through the entire list of required collision checks versus transformed 3D models in this one single video, but we'll see how likely that actually is to happen. So I'm going to start just defining a bit of some properties of this thing. So a transform model is going to have a triangle mesh. That is going to be a reference to a collision, like a regular triangle mesh that we've done before. We are going to give it a position in space, and I'll give this a default value of a new vector 3 with 0, 0, 0, so no transformation, no translation in space. And we're also going to give it a rotation that you can pass to the constructor. And again, I will give this a default value. This is going to be a matrix 3. And that is going to be the identity matrix 3, so no rotation on any of the axes. And I suppose, for what it's worth, specifying default arguments to the constructor here sort of hints to what type they are expecting. If there was any uncertainty about like what types you're supposed to pass in for like the rotation value or whatever. Anyway, we can say self.mesh is going to be the mesh, self.position is going to be the position, and self.rotation is going to be the rotation. And there are other things that you could supply to this. If you want like an entire hierarchy of transformations with like one transform model is like parented to another, you could like save a hierarchy of like parents and children models. But I'm not going to do that. I'm not going to put these in a hierarchy right now, aside from, you know, the octree that the triangle mesh is sorted into. Next, I'm going to write out just an entire list of things such as static check point. This is things that you've seen a million times by now, and I'm not going to waste any of your time by typing these all out one by one. So instead, I'm going to cut away to when I've just basically declared the functions with no body, no code inside them, and then we can skip to the fun part of actually implementing this. So I'll be back in a second. Alright, I have outlined all of the test collision shape methods for the transform model class, point, spheres, abs, and so on. The only exceptions sort of are that I have filled in check mesh and check model with return false. We are not going to be detecting collisions against those because those are going to be heinously expensive to like the extreme of seconds per frame instead of frames per second. And I know I've written some less than optimal code for the sake of readability so far that will be addressed later on in the future in the optimization video that I keep talking about, but I think that's a step too far for me. I have also gone and upgraded some of the, upgraded the tests. So we now have a call test model class, and that's going to allow us to play around with a transform model in space for collision purposes. What fun. And I've also made a small change to the way that they're actually set up. So instead of putting the secondary collision shapes on like Z, X, C, V, B, the bottom row of keys on the keyboard, I realized that there have ended up being a total of 10 collision shapes. So number pad 0 through 9 and the number row on the keyboard 0 through 9 is going to bring up each of the collision shapes. And the test model class is going to be generated with a random position and rotation. And as I say this now, I realize that some people like to develop games on laptops, and not all laptops have a number pad. I hope that's not going to be, like, a problem. No one's mentioned it so far. The series has been going for 2 years, so I hope that's not, like, that much of a problem. Anyway, one thing that I'd like to add to the top of call transform model before we move on to the actual collision shapes is going to be another method, and I'm going to call that static get transform matrix. And that's going to simply return a transform matrix with the rotation and position combined into a single world matrix. And this is going to look a lot like any other, like multiplying a position by a rotation or anything like that. Well, we're just going to return self.rotation.get rotation matrix, and we're going to mul that against self.position, which is a vector3.get translation. No, get translation matrix, and that's going to return our world matrix, or a transform matrix. GameMaker calls it the world matrix in a shader. Some other 3D systems call it like the model matrix or the object matrix or that kind of thing. But that's going to be our get transform matrix. I'm going to commit this to GitHub to keep our source control overlords happy, by whom I mostly mean me, because I think it's important to use source control correctly. And now we can actually get on to implementing these 3D collision shapes. So checkpoint is going to be first up. I'm going to first, and this is going to be common in every single one of these, I'm going to first say our inverse is going to be self.getTransform matrix, and I'm going to invert that with the .inverse method, and that's going to, well, you already know what this does. It's going to take the world matrix and get the inverse of it, and that is going to allow us to untransform the point that we're checking against, and I can declare another variable that's going to be var untransformed is going to be a new call point, and this is going to be the game plan for every single one of these. So we're going to get the world matrix, the inverse world matrix of the transform model, and we're going to untransform the shape in question in accordance with the inverse transform matrix. So I can say new call point, which takes a position of inverse.mul point against the original point's position, and that is going to construct a new point relative to the untransformed model, and we can check that for collision, and we can from here simply say return self.mesh.check point against the rather not the original point but the untransformed point. And you could also equal and oppositely say return untransformed.check mesh against self.mesh. It doesn't matter. 6 of one, half doesn't know the other. I'm just going to say self.mesh.checkpoint just in all of these for the sake of consistency. So if I were to run this now, this would actually be a little bit anticlimactic because, as you may remember, the triangle meshes in the system do not have a concept of something being inside or outside them. It's only going to detect 3D collisions with something that is overlapping one of the triangles, and in the case of points, that is going to require that the point be exactly flush against one of the triangles, which is going to be nigh impossible with something that has a rotation like this. And we're not detecting a collision now. That's not because this code is broken. That's just because the collision point is not lying completely flat on one of the triangles. If I were to do a little bit of... Oh, what do we want to do? Do a little bit of removing the random position and rotation of the triangle mesh. Then we would be able to detect a collision between the call point and the triangle mesh. If I were to move the tree around left and right, up and down, forward and backwards, you would see the collision going away and coming back. That would also work if I were to rotate this thing. I didn't explain how the rotation controls work with this thing. I, JK, and or IOP on the keyboard and JK and L, and that's going to allow you to rotate these things on one axis or the other. Something gimbal lock. I am not going to do quaternions in this project just for the sake of this example. Okay. So that is transform model checkpoint. I'm just going to commit this real quick. Probably not going to draw attention to that every time I do that for each of these shapes, but let's move on. So let me just copy and paste the inverse code here, because it's going to be exactly the same in every single one of these. Check mesh and check model don't need that because we are not going to be implementing those. Check sphere is up next. So if we want to untransform the sphere, this is going to be basically the same thing as untransforming the point. Var untransformed is going to be a new call sphere. The position is going to be, again, inverse.mul point sphere.position, and the radius is just going to be sphere.radius. So no scaling. If you were trying to do this with a uniform scale, you would need to multiply the sphere's radius by that uniform scale. If you were trying to do this with a non-uniform scale, that would be an absolute nightmare, and you would also have to implement a collision shape of an ellipsoid and transform a sphere into an ellipsoid, which I really don't want to do. And at the end, return self.mesh.check sphere against the untransformed sphere. I replaced my old keyboard recently, and I'm like still not used to the thickness and height of the keys, and as if I wasn't bad enough at accuracy in typing to begin with, it would frequently take me like 3 or 4 tries to spell words like that correctly. Now it's even worse. So we're going to generate a call transform mesh with a random position and rotation. I'm going to ask for a sphere, and I'm going to move this. You know what? I should probably like actually try to have this transformed model spawn somewhere that's like a little closer to the origin, so I don't have to move it around as much. Anyway, we can move the tree in and out and up and down, and we can do like rotations, and we can do other things to this tree. And we are going to have the tree correctly detecting collisions with the sphere. All right, that's great. All right, next we are going to be dealing with check AB for a transform model. So we're going to be getting the inverse of the world matrix, inverse of the transform matrix as usual. The way that we're going to do this is going to be a little bit different. Instead of creating a new call AB for the untransformed AB, we're actually going to create a new call OB for the untransformed shape. That's because when you rotate an AB, it's not going to remain axis aligned. It's going to be rotated in some way. It's going to have some kind of rotation, and we're going to need to turn the AB into an OB. I'm pretty sure we've done that in the past when we did collisions with ABs and OBs and other wonderful Dr. Seuss esque collision shapes. But let's start with the position. So the position is going to be inverse.mul point against the AB position. So that's going to be not too different from what we've done before. We're going to just transform the position in space. The size is going to be ab and did I call it like .half extents? I called it that in my test project. That's a bit of an unwieldy name. I did. All right. Should have just called it size or scale or something for brevity, but whatever. And the orientation for the oriented bounded box is going to be just the rotation component, the orientation component, so the upper 3x3 minor of the inverse transform matrix. And we can grab that by saying the orientation for the OB is going to be inverse.get, get orientation matrix for the OB. And from here, we can say return self.mesh. And remember, we're not checking an AB anymore. We're checking an OB like this. And the shape that we're checking is the untransformed model. All right, the untransformed block, rather. So once again, we're going to bring up one of these things. Once again, I wish I had it spawn closer to the origin and an OB. Let's see, move you down. All right, wow, performance is definitely taking a bit of a hit here. This is going to be due to the inefficiency of OB versus triangle mesh, I think, more so than the inefficiency of OB versus like the mesh itself, because we haven't actually written any complicated like code here. Let's see, that works for position. If I were to rotate you, oh man, it's not quite seconds per frame. but it's definitely less than ideal. There are ways that you can potentially optimize this, but I think even with some very, very fast GML, it's going to be difficult to make this run at playable frame rates for any real purposes. All right, enough of that. Let us commit the next change. And checking an ob against the transform model is going to be very much the same. So var untransformed. This is going to be a new call ob once again. The position is going to be inverse.mul point ob.position. We've seen this before. The size is going to be ob.size. I did just call this size, right? I'm pretty sure I just called this size. Yeah, I should have done that for ab. Make typing this a little bit easier. And the only difference here between check ab and check ob is going to be that instead of just grabbing the inverse matrix's orientation and just leaving it at that, because abs don't have a rotation, they are aligned to an axis, the rotation is just the identity matrix. We are going to take the ob's orientation, and we're going to multiply that by the inverse.get orientation matrix. And is that the correct number of parentheses? It is. So we're going to take the existing orientation of the oriented bounding box, and we're going to combine that with the orientation of the inverse transform matrix. And lastly, return self.mesh.check ob. That is literally the same line of code as last time. I could have copied and pasted and made my life a little bit easier. And we're going to run this. By the way, you probably assume this, but I will just go out and say that the reason that, like, I say, let's put an ab on the screen, and then it's a couple seconds before it actually, or the reason that I say, let's put a mesh on the screen, and then it's a couple of seconds before it actually happens, is because building the actual hierarchy of this thing is a little on the slow side. What do I need for ob? This is going to be 8 on the keyboard. All right, so again, we are getting a very Microsoft PowerPoint-esque 20 frames per second or so, and I can move this through the box, and we can check if there's a collision or not. I can rotate U, and we can check if there's a collision or not when we like swing this tree around like a hammer, because we can do that because we're in control of what happens in this game, apparently. So check plane seems to be next on the list. This is going to be where things get a little bit interesting. This is a little bit more complicated than the ones that we've done so far. We're going to have to actually do a little bit more work to correctly transform the plane's distance. Transforming the plane's normal is not going to be that bad, but we're going to have to like derive the distance. And this is something that we should have done before. We should have, in fact, I think, let me look at check ob. Let me look at ob's check plane. Okay, we actually didn't do anything like this for ob's check plane, although you could have. So we're going to, let me say var point, and this is going to be plane.normal.multiply by plane.distance. This is going to be just a point on the plane. We're going to need to save this for later. We're going to need to use this when we want to figure out the distance of the plane from the origin. And we're going to want to untransform the point, so we can say point equals inverse dot mul point, and that's going to give us a vector 3, which represents a point on what is going to be the untransformed plane. What do I want? Point. So this is a vector 3. This isn't a call point. Just in case I need to clarify. Next, we're going to untransform the normal. This is going to be relatively easy. We can say our normal is going to equal inverse dot mul vector, and we can pass in the plane. No, not the point. The plane dot normal, and this is going to untransform the plane's normal. Our distance is going to be point dot product against the normal, and that is going to give us the new distance of the plane from the origin. And now we can say our untransformed is going to be equal to a new call plane, and the normal is going to be normal, and the distance is going to be distance. And from here, it's just a simple matter of saying return self.mesh. dot check plane against the untransformed plane. And I'm pretty sure that we've done something that looks a lot like this so far, like elsewhere in this series. I can't remember exactly where. Taking the like calculating the point on a plane and then transforming the plane in some way, and then taking the dot product of the point against the new normal to figure out like the new distance from the plane. Anyway, let me run the game and let me bring up a. I'm gonna actually bring up a plane on the on the side that I can move around. That's gonna be numpad 4, and a transform model is going to be 10. And from here I can rotate this, and we can detect a collision between the plane and the tree when it goes about here. Unfortunately, I can't like exactly see where it starts and stops. Where are you? There we go. All right, so you can see that the shape overlap text appears on the screen when I'm about here, and when I have a better visual on when the overlap starts and stops. And if I did want to reverse it, I could take a transform mesh and move this around. I can move this up, down, rotate it around. We have collisions detected with the plane. That's a lot of fun. All right. So capsules are up to bat right now. After all the trouble capsules gave me in previous videos trying to get 3D collisions to work with them, I'm pleased to report that untransforming a capsule to do a collision check against a transformed triangle mesh is not that bad. So we can take the inverse. We can take var untransformed is going to be equal to a new call capsule. The line start is going to be capsule, and the order here matters. So I've really gotta make sure that I say inverse dot mul point capsule dot line dot start. The end point is going to be inverse dot mul point capsule dot line dot finish, and the radius is going to be capsule dot radius, and return self dot mesh dot check capsule against the capsule. And we can run the game. By the way, fun fact about Game Physics Cookbook, the book that I've been citing frequently throughout this series for where I learned a lot of the 3D collision math. It actually had planes versus transform meshes wrong. It did not correctly account for the plane's distance from the normal. I've submitted an issue for that on Gabor's GitHub, and hopefully he will at least finish that in the version of this code that is on his GitHub. This does not look correct, and I have a feeling that's because I am, instead of checking for collision against the untransformed capsule, we are checking for collision against the original capsule. So yeah, if the tree had no transformation and the system thinks the tree always has no transformation, then of course the collision will always be detected. So let's try that again, and we can move the tree up, down, forward, back, left, right. We can spin it in circles. That's not a very useful axis to spin this around, is it? There we go. Again, not super performant. It's better than like AABBs versus capsules, but it still leaves a lot to be desired. All right. So that's check capsule. Let's go and log that one. Next on the list is check triangle, and this is going to probably start feeling pretty repetitive right about now. And while I try to keep sections of the video in which I say things like figure it out yourself to a minimum, we've really been doing the same thing for probably most of this video, and I don't really want it to get all that repetitive. I am going to do a little bit of assignment homework here. It's not like I'm actually going to grade this or anything like that, or good on your kids if you don't do it, but your homework for this video is to implement check triangle and check line yourself. It's really not that different from anything else that we've done so far, particularly the last one. And I'm tempted to say that for extra credit, you can also do check ray yourself, but that's actually going to be a little bit different because in addition to just figuring out whether or not the ray hits the transform model, you're going to want to figure out whether, where the hit information is, and you're going to want to make sure that that's correct. And while it's not hard, I do at least want to have that shown off in the video. So I can go and say var untransformed is going to be a new call ray. The ray's origin is going to be inverse dot mul point by the ray dot origin. The ray's direction is going to be inverse dot mul vector against the ray dot direction, and that's going to be our untransformed ray. Remember, origin has a position in space. When you untransform or transform a position in space, you need to account for translation. Direction has no position in space; it is only a direction, so you can you only have to account for rotation and no position. And we are going to want to construct a temporary hit information struct as well, or at least I'm going to want to for my implementation of this. I'm going to say var untransformed hit info is going to be a new raycast hit information struct, and I'm going to say if self.mesh.check ray with the untransformed ray and the untransformed hit. All right, GameMaker code completion isn't picking up on that one, so untransformed hit info. Then we're going to want to take the hit information from the untransformed hit information, and we're going to want to, am I really going to say this, untransform it into its original position in space, so that we can actually figure out the collision normal, the collision position, the distance from the origin, and that kind of thing. So we can say var point is going to be equal to, and I'm going to also var transform equals self.get transform matrix, and there's no need to calculate that twice, so we can say just inverse equals transform dot inverse. So point can be transform dot mul point against untransformed hit info dot point. Var normal can be transform dot mul vector untransformed hit info dot normal. The distance, this can be ray dot origin dot distance to the, is it distance 2? It's distance 2. Ray dot origin dot distance 2, the point of contact. I do realize now, 30-something videos into the series, that saying hit info dot update and having to pass it the distance, the collision object, the point and the normal is a little bit like redundant, because you can always derive the distance from the point. Actually, no, you can't, because the hit info struct doesn't know where the original ray came from. All right, never mind. After this, we can return true because a raycast hit was detected. Otherwise, return false. And if I were to now run the demo and bring up a transformed object, we can raycast into it, and we can detect where the raycast hits into the transformed object. All right, that's a lot of fun. I can move my mouse cursor all around this thing. I can look at the bottom. I can transform it in other ways. I can move you left and right, and the raycast hit location is correct. I can rotate this around, and the raycast hit location and normal is still correct. Rotating it on the z-axis doesn't really accomplish much, does it? Because it's the tree is kind of aligned with the z-axis, just like in general. Anyway, so that is going to be transformed model versus, and that's going to do it for 3D collision math. So once again, check triangle and check line. I'm going to leave that as homework. I'll put homework in quotes because, again, it's not like I'm actually checking to see if anyone's doing this. And in the final version of the code that's on GitHub, I will implement these anyway, just for the sake of completion. So next, there's a couple things that I'd like to do. I've been talking about optimization strategies for this code quite a lot, and for good reason. As I've said many times, I prioritized readability over swiftness of code. Let's just say that it leaves a lot to be desired, and I'll be getting into what some of those things are later on. There's also the matter of height maps. I said I'd talk about height maps. I'm not going to be treating height maps like a true collision shape, and I'm not going to really be doing any actual 3D collision math on them, but since you often have things like figuring out where the player belongs on the ground going hand in hand with 3D collision systems, even my like what I'm going to call my cheating solution for height map terrain is probably going to like fit in pretty well with the rest of this, just because it's like it's a similar component of a video game. There's also the matter of some different collision hierarchies that you can use. I use an octree, largely because I can use that for a triangle mesh, and I can also use it for like the collision worlds at the same time. There are other collision hierarchies that you can use. Some of them lend themselves to some types of like shapes and collision worlds and that sort of thing better than others. The ones that I have in mind are going to be quad trees, which are usually used in 2D collisions, but in certain circumstances in 3D collision worlds you can use them as well, and spatial hashes. If any of you are friends with the Snitter, you will probably know that he's a fan of the latter. After that, I haven't decided on this. You can all let me know what you think, but it's possible that I may bring camera frustum checking into this, but it could be useful for some people, and if anybody wants to make a case for it, we may tack that on at the end. And then, of course, coming in and wrapping up the series, there's going to be an Act 3 collision world where I'm going to make something that looks sort of like an actual game for this soon. And I don't think this will have happened by the time I put these videos out, but soon I will put all this into practice because my current Let's Make a Game, project is going to be in need of a 3D collision system, so I'm going to get to put this into practice there. Unless anything goes catastrophically wrong. So I think that should be quite a bit of fun. So, that's going to do it. My name is Michael. I like Wizards and Dragons making games. If you want the code for this, look in the GitHub, look in the video description for a GitHub repository. Look for the 0.29 release. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places as well. I would definitely appreciate it if you wanted to contribute anything, because these 3D collision videos in particular definitely take a lot of work to make. I try to post about 2 game dev videos a week, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, Gamer Player, Harold Guidry, Manta Ray, Sindra Larson, Squarecrow, Vitro V, and Zengiment for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.